Welcome everyone to Guided Study Group Week 2 of Math 140. We're gonna have these sessions at this time every week, and I'm just gonna run them in kind of like a similar way. I'm just gonna briefly review the questions, the sessions that we learned that week, and then I'm not gonna like repeat the lectures or anything. So just gonna go through like some of the main points really quickly, and we have some of the example problems. So the way that I do it is usually similar to what you guys should expect, maybe like in the quiz or homework or exams, because I all like summarize them from previous semester and also from my own class when I take 140. So hopefully I'm not gonna bore you guys so much. If you have any questions anytime during the semester or like even during the sessions, if it's during the sessions, you can feel free to just like type it in the chat room so that I can stop and then maybe like explain a little bit more if you guys are lost. My email is hgt5011. So if you have any questions regarding like materials, feel free to email me. Even though I'm the tutor, I wouldn't be interfering with your grades. So anything related to like homework submissions, examity, how to schedule your exam, what is my grade on practice exam, and all of that kind of thing. Do not email me. Email Dr. Bang Seung-hoon or Dr. Katazina for it, because I wouldn't be able to help either. I can only forward it to them. So yeah, so let's get started. Any questions with whatever we are doing here before I get started? I mean, all of these sessions is gonna be recorded for a while. Now we have 8 people. This is the first time in history. Yeah, so you can put your PSU email in the chat, or I will ask you guys again to do it at the end of the sessions. And it's kind of like clear here, type your PSU ID. So let's get started. We have 3 sessions today. So first one is 6.6. So 6.6 is where we start working on inverse trig functions. And so I kind of like have a very brief table of like summarizing them. And these are the things that you guys should pay attention to for inverse, because inverse function, for a function to have an inverse exist, it needs to be one-to-one, and these are the domain and range that will ensure the fact that it's one-to-one functions. So we have the domain of sign. So domain is the possible value of x in here, and the range is the possible value of the entire function. So inverse sine of x can only have the value between negative pi over 2 to pi over 2 on the unit circle. So the value can only be from here to here. And the derivative of that function is also there, and then we have related integrals. So it's kind of like a nice summary. It's like a lot of information in this table, but I guess if you guys already watched the lectures, I assume it should be the case, then you guys should be able to like figure kind of manipulate through this table pretty easily. Some of the very rare one that I hardly ever see, but you should still know, is cosecant. Sometimes we'll see secant, but it's not a very significant part. Usually we're just gonna see like inverse sine, inverse tangent, inverse cosine, and all of that. Maybe when you're doing like integrals, like integration by parts or trig integral or those kind of thing, you're gonna see inverse secant, and then cosine and cotangent. So just like kind of some of the how do they look graphically is that we have okay, -1 and 1. So just kind of like demonstrate the general way of how these function looks on the graph. And I found like it's a very easy way to remember the material. So instead of remember that table, so this is sine, inverse sine. Then we have inverse tangent. Inverse tangent, as we see in here, is in between negative pi over 2 to pi over 2, and it's not including the endpoints. And the domain is from negative infinity to positive infinity. So what happened here is that we have pi over 2, negative pi over 2, and this is the graph. It will approach on the two ends, but it will never reach there because our range doesn't include the endpoints. Oh shit, I don't know. Okay, so the inverse secant. Inverse secant is kind of like a very odd one. I doubt the fact that you will be asked about these graph, but it's always good to know. So this one is -1. This is going to be pi. Oh, we don't need this part. And then we have something here is 1, where we're gonna have this thing approach it. So if we look at the range for inverse secant, is going to be from 0 to pi over 2 and then pi to 3 pi over 2. So yes, we need that, right? So this is pi over 2. So it's bounded by that value and it will not exceed it. And then it's 3 pi over 2. So it's like an odd one, but it's always good to know. But inverse sine and inverse tangent, definitely you should know. Then we have something called the right triangle relationship. So it's kind of like the way that we determine, okay, say if you're given a question asking like, what is inverse sine of 2x? So what we're going to do is that we have a right triangle. So when we have sine and cosine, the first thing that comes to mind is that it's kind of like a trigonometric relationships. So it have to deal with right triangle. Now we have inverse sine is 2x, which means the sine of the angle, whatever angle, if we say that thing is alpha, so sine alpha is going to be 2x. Now, if this is alpha, alpha has to be an acute angle, then so that it have the value of sine existing. So inverse sine of, no, we have sine of that is 2x. Sine is opposite divided by hypotenuse. So we have 2x, and then this is 1, and the other side is just 1 minus 4x squared. So I think you guys should be really familiar with that. So inverse sine, say if they're asking you like cosine of inverse sine 2x. Now the answer is going to be square root of 1 minus 4x squared. So it's adjacent divided by hypotenuse. So before I proceed to the first example of today, is there any questions so far? It's just like a quick review of whatever is going on in class in the sessions. Okay, if not, I'll go to the example. So it seems like we've been on a good page for this, so let's briefly go over it. We have tangent of inverse cosine 3x. And yeah, if you're like watching it online or you're joining it with me, feel free to like mute me if you want to try it out on your own, or maybe we can go through it together. So we have a right triangle. Inverse cosine is 3x, meaning if we have this is the angle, this is 3x, this is 1, and this is 1 minus 9x squared. Therefore, we have tangent of that is going to be 1 minus 9x squared divided by 3x. Now, similarly, we're asked to find secant of inverse tangent, 12 over 5. So, again, a right triangle. Now, we have tangent of that is 12 over 5. I don't really care about the ratio here. Just the tangent is 12 over 5. So just say it's going to be 13 by Pythagorean theorem. Then we have secant of that. Secant is 1 over cosine. So if cosine is adjacent divided by hypotenuse, secant is going to be hypotenuse divided by adjacent. So the inverse of that. So 13 over 5. So that is my answer for these two small questions. Is there any problem with this thing so far? Okay. So let's go to second example. So find this limit of x approaching negative infinity, inverse cosecant of that. So first we have to find what is this limit before we can use inverse function to give the value. So a minus x square root of 3 divided by square root of 4x squared plus 17. Now this one is, okay, let's take the inverse cosecant, inverse cosine outside. What we have so far in here is um 4x squared plus 17. Now, if we want to solve this, now if we plug in negative infinity in, what we have is that we're going to have negative infinity over infinity. And obviously it's not giving us anything. It doesn't tell us it was like a number, or it can't even be 0, or is it going to be negative infinity. So what we're going to do is that we're going to try to use some of the techniques that we learned before to find limit. So here if you look at the fractions, the highest power of the numerator and denominator is the same, because here's the highest power is 1, x to the 1, and here is x to the 1 as well. So when we take x out, what we have is 8 minus square root of 3 over, a over x minus square root of 3. And the other one is, when you take x out here, this is where you have to be careful, because when you have 4x squared plus 17,
rule.
I don't think you can use it yet in this class, because I mean technically you can, because no one is going to be able to know if you're using it or not, because most of the questions is derivative. Most of the questions is multiple choice. But then at the same time, are you 100% sure that you can use have you learned about the seventh indeterminate form of limit that we can use the Hospital rule for? Then I mean in this case, then you can use it. But this is the technique that I'm showing you. It's before they invented the Hospital rule. So if you want to use the Hospital rule, that's completely fine. But I don't know if everyone would know that rule. So the Hospital rule is just, yeah, the Hospital rule is just applied for the 7 indeterminate form: infinity over infinity, 0 over 0, infinity minus infinity, 0 to I think infinity, and then we have 1 to the infinity, and then also infinity to the 0 or something. There's another type, which is I couldn't remember at the top of my head, but that is the materials that you guys gonna learn in, I think, 2 weeks or so. So, or maybe at the end of midterm 1. I don't know, but I don't remember the time. But yeah. But in this case, and for anyone who doesn't know how to use the Hospital rule, I think it's a very good practice to solve it the other way. It's always better to I might need to mute one of you. Okay. So what happened here is that when you have x is the negative number and you want to take it out of the square root. So when we take x squared out of the square root, is that what we end up having is absolute value of x, because this part is a positive number on the left. So the thing on the right, if it wants to be equal, it has to be a positive number as well. The square root itself is a positive number. So we have to end up with something here is a positive, which is absolute value of x. But if we keep absolute value of x, it doesn't help us solving the problems. So what happened is that this number, since x is negative, the absolute value of x is going to equal negative of x. So 4 plus 17 over x squared. So another thing we learned from here is that absolute value of x is equal to negative x if x is smaller than 0. And it's going to be equal to x if x is bigger than 0. So in this scenario, what we have is that because x is approaching negative infinity, it's a negative number. So when you take it out of the square root, then it ends up going to be negative of x multiply square root of 4 plus 17 over x squared. Is there any problems with this part? Before we proceed, I just want you guys to make sure that you guys understand what I'm saying. Therefore, we have 4 plus okay, 17 over x squared. So we have that is inverse cosine of. Now we have x and negative x. We kind of like we can cancel something out. So limit of x approaching negative infinity, a over x minus square root of 3 divided by negative square root of 4 plus 17 over x squared. So now all we need to see is that when x approaching negative infinity, this part is 0. This is also 0. So what we end up having is inverse cosine of negative square root of 3 over negative 2. So negative square root of 4, which is negative 2. Or is inverse cosine of square root of 3 over 2. Now it's where you're going to use the domain and the range of the inverse function to solve for this. So the value of inverse cosine, if we get back to that table, the value of that is, the range is bounded by 0 to pi. So if we draw the unit circle out, the value of cosine, so this is 1. Oh God, what's wrong with this technology thing? So this is the cosine axis and this is the sine axis. So this is the angle. So that ends up giving us pi over 6. If it's like half, so if it's half, it's going to be up here, which is going to be pi over 3. But it's square root of 3 over 2. And if you're asking me like why you know it's pi over 6 or pi over 3, but it's not like pi over 15, there's going to be a table at the end of your book. It's going to give you like the general, like some of the special angles. That's how I figure it out. But to distinguish between pi over 3 and pi over 6 is using this unit circle to figure it out. So if there's no questions with this part, I'm gonna proceed with example 3. So before I do this one, I'll give you guys like 30 seconds or a minute because it relates to the materials that you guys learned last week, but I didn't go over. It's just kind of like my way of doing this class because it was first week. I'll let you guys figure things out on your own first before jumping in. But yeah, I'll give you guys like a minute or 30 seconds to work on it. In the meantime, if anyone wants to put their PSU email in the chat room, that'll be awesome. Just type it like other people already did in the chat room. Okay, cool. So I'm gonna go ahead and solve this one. Just a quick hint to anyone who is struggling to find what is the star is when you start to use log differentiation, what I think you guys might learn last week, and then we're gonna use the derivative of inverse functions to solve it. So we end up having fx equal inverse tangent of x to the 2 of x. Now, if we use log differentiation, because here you can see the fact that this is a function of x to the power of another function of x. This is a complicated case, but it's a general form of log differentiation. So that's how we're going to solve this. So we have log, or not, that log is used in scientific thing. So we're going to 2 to the x ln of inverse tangent x. Therefore, if we take derivative of both sides, you're going to have f of x over fx going to be 2 to the x. So this is product rule, so this should be ln of inverse tangent of x plus 2 to the x. Now, derivative of inverse derivative of ln of inverse tangent. So first off, all of the general form of ln of u prime is going to be u prime over u. So u here is inverse tangent, and then u prime is what we're trying to work on because it's the 1 plus x. Does it have the square root? I don't think so. Let me check it back. Sorry, I kind of like not remembering. Yeah, it doesn't have the square root. So we can ignore that part. Okay. So now we just need to simplify, or you can just like make sure that put everything with not related to f prime of x on the left and everything else on the right. So we have fx is inverse tangent of x to the 2x, 2 to the x. It's not 2x. So we have 2x ln of 2 multiply ln of inverse tangent plus 2 to the x over inverse tangent of x multiply 1 plus x squared. So that is my answer for this. So two things in here, log differentiation and what is derivative of inverse tangent. So it's not something new, but you might have not expect that, okay, they're gonna give like so many things in one questions. But that is the general way of like we solving these problems. In reality, there's no one's gonna give you like, okay, just tell me what's the derivative of that. Usually we have to translate word problem into mathematical symbols, and we have to try to figure out these things on our own. And usually it involves more than one technique. So that's all I have for 6.6. Now we're gonna go to 7.1. So 7.1 doesn't have that many things. It's integration by parts, and also kind of like this is another nice summary of all of the general formula that we've had so far since Math 140 and until now. So we have yeah, I will let you guys have a look on this. The new things maybe, and then some of you might have forgotten this one and this one. It's not that common anyway, but it's going to be common in Math 141 when we start doing with integration. The new one is maybe integral of tangent x and integral of cotangent x. But we're gonna, as long as we do a lot of practice, you guys gonna remember them naturally. So integration by part is where we have integral in the form of u dv. So u as like a function, and dv is a derivative of the second function. So usually integration by part, we apply it when you have an integral of two different types of functions. So say if you have exponential with polynomial or trigonometries with log, those things kind of like that. Sometimes it can be really apparent, like you can just look at the questions and you see, okay, that's log, or another one is trigonometry. Sometimes it can be a little bit trivial. So say if you have like this tangent x dx. Obviously when you look at this, it's only tangent x. But if you can rewrite it as tangent x multiply 1 dx. Then it's gonna be trigonometry up here, and this is polynomial. So sometimes it can be a little bit subtle to notice, but we're gonna work on those things and try to figure out. So there there's an order that you choose what is u, and it's gonna be inverse. It's gonna follow the order of inverse trig, log, algebra, or polynomial, trig, and exponential, and it's just isolate. One of like kind of like the abbreviations to remember it. It's nothing new here. If you watch the lectures, this thing should be kind of a little bit trivial now. So let's start it with example 4. So this is a quick one. So the order you're gonna choose the u is going between exponential and trigonometry. We're gonna choose use at trigonometry as the t in isolate. So we have u is cosine of x. Let's call this thing I to just save my time, not repeating it. Du is going to be negative sine x dx. dv is e to the x dx, whatever left except for cos after we take cosine out. So v is going to be e to the x. Now your value of I is going to be e x cosine of x minus, with a minus is a plus, e to the x sine x dx. Now again we have another integral, so I'll call this I1. So what we have is that we're going to do the same thing, u equals sine x du. You can use like u1, u2, v1, or v2 if you don't want to confuse with that. But the way that I try to organize this is that I try not to get confused. So v equals e to the x again. So now I1, you might find the fact that maybe it's like a never-ending loop, but it actually will, and this is what happened right now. So it's giving you the thing that looks exactly like the original. So this is I. So what happened if we combine these two is that we have I equal e to the x cosine of x plus e to the x sine of x minus I. So obviously here, one of the things that you can do if you already get to this point is that you're just going to move this I over to the left. So we have 2I equal to this function. And then we have I is just going to be 1/2 of this. So that is my final answer for these questions. Any problems so far? It's not especially tedious, and it actually falls in like a lot of cases when it dealing with if you have like exponential and trig at the same time. That usually is the case. Sometimes you can have this is becoming a plus I, so it's gonna be your I doesn't have a value because then you're gonna have I and equal something plus I. So your I is just does not exist. So with that the case, I'll go to example 5. So find the integral from 1 to 2 of log ln 2x over x squared. I'll give you guys like 30 seconds to work on this. You guys might have been really fluent in the technique already. But yeah, so if anyone have any questions so far with what I've been going over, let me know right now so that I can explain it again. If you want to work on this together on your own, I'll give like a minute to work on it. It's not hard. Just using the order that we have isolate. Okay, so we're gonna solving it. So in the order we have is we have log and polynomial. It's just the fact that here with we can rewrite this as ln of 2x multiply x to the -2. So that's where we're dealing with negative power. So I also want to introduce you, if any of you haven't known, this is another way that we can write it. It just make our life easier when we have like these thing to take derivative of, because obviously if you have it in the form of like to the negative n, you can use the one that say if we have derivative of this, it's going to be negative n multiply x to the negative n minus 1. It makes us life easier than using the kind of like the fraction form to solve for it. So here, again, just follow the order. Then we have du is 2 over 2x. Here, be very careful because ln of u, and we take derivative of that is u prime over u. So remember, there's a 2 up here and do not forget it. Some of you guys just missed it before I saw in the class in the spring semester. So just make sure that we have v here. So here we have negative and negative 1 is negative 2. So n is gonna be negative 1. So this one is negative 1 over x. So it's gonna be, we have, let's call this thing I again. So we have I is negative 1 over x, ln of 2x. And a minus is plus 1 over x squared dx from 1 to 2. And this one is also from 1 to 2. So what we end up having is now we have ln of 2x. And this one is just basically another, it's just dv. So integral of dv is just going to be v. So it's from 1 to 2. So what we end up having now is just plug it in and solve for. We're given 2 plus 1. So what we have here, I don't remember what is the, there's going to be half plus actual answer for this is anyway, 4 to, oh, this one we can take the negative out, so it's going to be, yeah, it's just half, because negative 1/2 of ln of 4 plus ln of 2 is going to be ln of 2 minus, take the minus out, and then we have ln of 4 to the half. Take this half inside, so that's what we have is just ln of 2 minus ln of 2, which is just 0. So that is my answer. Here again, integration by part is not that hard. Just keep track of your negative side, because here you see like here's a negative and here's a negative. Sometimes when you will lose track of it, and especially when it's a definite integral, they only look at the final answer as it should be a number. And if you mess up anywhere in between, the entire answer for sure is gonna be wrong. So yeah, that's example 5. If we are good with here, let's go to the next one. Again, 30 seconds. It's kind of like a little bit tricky here because we have polynomial and a trig functions. But the trig function here, we don't have the derivative of tangent square. There's some small manipulations that you guys need to know. Oh, can I go back? Okay, sure. So yeah, what is the questions here? Oh. And just do you have any specific questions for this part? Or if you just want to copy this, that is fine. For this thing, the negative half in front of that. Okay. Yeah. Do you have questions with it, or? Yeah, the negative half is in front of ln of 4. And yeah, I don't quite understand what the question is. Yeah. So one of the kind of property of ln of a to the b is that you can just is going to equal b ln of a. That is one of the property of log function. Okay. Yeah, that's one of the property. If some of you might have forgot from last lectures, but that's fine. Now we know the fact that we need to improve on that. So that's a good thing actually. Okay, now we're gonna go back to these questions. So I'm gonna go ahead and solve it. So here when I said we have, so say we have here polynomial and trigonometry. If we follow the rule, we're gonna put u equal to x and dv is tangent square x dx. But no one know what is the integral of tangent square. So the small manipulations that we have to make here is that we have tangent square plus 1 is secant square x. And this one is gonna come, I think this one is what you guys learn from, I think, very general trigonometry, but I think a lot of us is like adult learners, so that's might have been a long time ago. So it's a good way to review it by mentioning it in some of the practice problems, just not making it like, okay, you have to remember this. If we apply it, make it easier to remember. So tangent square of x plus 1 is secant square. So we can rewrite this as x secant square minus 1 dx. And so here, now we have two small derivative, integral that we can solve. And the one that have negative x is easy because it's a polynomial. We only need to care about the one on the left. So what we have here is instead of tangent square, now we have secant square. And we know what the integral of that one is. So du is going to be dx, and then dv, and then v. Integral of secant square is tangent of x. So what we end up having, put this one as I is going to be equal x tangent x minus tangent x dx from 0 to pi over 3. And then remember, you still have the extra x dx here. So what we end up having, and we have integral of tangent, a special one that I told you guys that you need to know sometimes, but it's not very specific. So that's going to be ln of secant x, and then we have this x over here. So integral of that is just going to be x squared over 2. And then we take plug in pi over 3 and 0 for each of them. So when you plug in pi over 3, we have pi over 3. Tangent of pi over 3, again, unit circle. So cosine, sorry, his brain thing is, this is cosine, this is sine. So tangent is sine over cosine. Sine of pi over 3 is square root of 3 over 2, and sine of pi over 3 is, cosine of pi over 3 is half. So tangent of that is just going to be sine over cosine, which is square root of 3. Now for secant, secant of pi over 3 is 1 over cosine. 1 over cosine here is half. No, cosine here is half. So 1 over cosine here is going to be 2. And then again, we have pi squared over 18, because it's 9 multiplied 2. And then when you plug in 0 for the rest, so you have, when you plug in 0 here, so it's going to be negative 0, and then negative ln of secant. So secant of 0 is 1 over cosine of 0, which is 1. So ln of 1, which is also 0. And then we have 0 over 2. So what we end up having is pi square root 3 over 3 minus ln of 2 minus pi square over 18. That is answer for this question. Any problems here so far? Yeah, I think these questions have a lot of things. First, you have to rewrite it, because you're going to be stuck at tangent square. rewrite it using this one. I think there's another one for cotangent. So cotangent square x plus 1 is going to be cosecant square x. Let me check it back. So it's cosine square plus sine square. Where did you get the x squared over 2? Yeah, it's from here. It's this part. It's the it's this part, right? We have 3 terms in this integral. Okay. Yeah, just make sure that you guys don't miss out anything. So from every step, make sure that you account and maybe like rewrite all of the terms that we need. So here, this part is coming from this term only, and this part is this term. So make sure that you guys don't miss any of them. So when we're done here, let's go to the last session of today. So it's trig integral. So this part is one of the part that I think is the easiest for midterm 1. Not like easiest, besides integration by part is the easiest. Because there's only that much of the things that you can use in these things. They're absolutely not going to be anything new. And all of the things that we need to use here, I already listed out. For this type of questions, I tend myself, from my own experience, is that I never actually remember them by odd or even functions, because kind of like in my high school and the way that I get the Vietnamese education is that we've been pushing through all these math to get the intuition. But again, the odd and the even one is a good start to get those kind of like intuition of, if you understand why we have to separate them into odd and even, and why we have different strategy for each of them, then that'll be a good start to get an intuition. So here we have 2 types. The first type is sine to the m multiply cosine to the n, and we try to take the integral of that. All that thing you can do is using U substitution, half angle identities, double angle formulas, and cosine square plus sine square is 1. So cosine square plus sine square is 1 is one of the most basic relationships for trig relations, so trigonometry relations. So that's one thing that you guys should always know. The double angle and the half angle identities are not that popular, but it's always a good way to solve them, especially when you have, like, I think Dr. Catcher say it as like sine and cosine both in even functions, that when you're going to use the half angle identities. The double angle formula might not be very helpful now, but I think in maybe next week when you learn trig sub, then that's going to be one of the very helpful tools to use. So these are all of the things that we're going to just use it. And then we have another form is integral of tangent to the m and secant to the n. So again, there's only that much of things that you can do. Use substitution, tangent square equals secant square minus 1, or just the one that we worked on earlier, tangent square plus 1 equals secant square, same thing. And some extra, sometimes you can get like extra, a little bit challenging questions to get some bonus point. So these are some of the things that we will use. So yeah, so that's this. We already know this. We already know this one from 140, even though we don't use it that much. Cotangent is just similar to tangent here. Especially remember here it's a sine. Here you have ln integral of tangent is negative of ln of cosine. So when you think about it, when you go from here to here, it's similar because ln of negative of ln cosine of x, you can take that negative inside. So ln of cosine x to the negative 1, or just ln of 1 over cosine of x, which is just ln of secant x. So not too much if you understand the relationship behind all of these things. It's just different way to rewrite the same thing. Yeah, so that's all we have. And let's go to the two last example, and then we're done for the day. So example 7 is find the integral from 0 to pi over 2, sine to the 5th and cosine to the 3rd. Now, if we look at the lecture notes, and also one of the way that I would say, if you don't want to just remember all 3 cases, just the first thing that comes to mind is that if you have all even, then you use the half angle identity. But if you have just one of them odd, you don't need to like separate them like both odd or one of them is odd. Just when you have at least one of them is odd is when you use U substitution. And you can U substitute, put U as sine or U as cosine. It's going to give you the same answer. In my opinion, I usually put U as sine because I don't want to do with the negative. When we have derivative of cosine, it's going to be negative sine. I don't want to do with that negative. It's just make my life a little bit harder. So when you do this U substitution, you do the change of variable. So from 0 to 1. Therefore, this I now is going to be 0 to 1. Sine to the 5th is U to the 5th. To take one cosine now, so what you have is cosine square. So you have du. So now we have the cosine square here. That's when we're going to use cosine square of x plus sine of x. Sine square of x is going to equal 1. So you can rewrite that cosine square as 1 over sine square or 1 over u square. Now, life is so much easier because now we just need to take integral of a polynomial. So u6 over 6 minus u8 over 8 from 0 to 1, which is 1/6 minus 1/8. What we have is 1 over 24. So not hard. It's just, yeah, as I said, we only have that many things that we can use. As long as you do enough of the practice, and I would highly recommend trying the practice problem on Canvas. The more that you do them, the more ready you are for the exam, because I already looked through all of them when I do previous planning for this course, and it's really helpful. If you want to challenge yourself a little bit more, try the even problems where you don't have the solutions for it. Yeah, that's just the case. Now, we're gonna go to the last example of today if we don't have any questions here. So same thing, there's only that many things that you can do. And this is actually in the practice problem F that I give out at the end of this session. So if you notice, the way that I run Math 141, it's different from Math 140. 140, you have a lot of practice problems in the book already, so I don't even give it out on my own. 141 tends to be a little bit more challenging, and it's really hard to make sure that the student and my learners understand all aspects of it. And the way to test themselves really easily, it's use my own questions. Because I noticed my old professor, not Dr. Katuzina, I didn't take the class with her, but my quiz questions and all of the practice exam that I was given out at that time is way harder than the actual exam, but it helps me prepare really good for the actual exam. Actually, I spent like 40 minutes on the final, which is super fast. I'm amazed at myself as well because I thought it's going to be super hard, but end up it's much easier than that. So it's a very good preparations. It's always good to know more than less. So here, again, that's all everything that we can use. So here we have both of them is odd in power. So one of the things we can do is we try to get rid of one of them. Because when you have secant to the 5th, it doesn't allow us to use secant square equal to tangent square. So we have to get rid of one of that secant. But we don't have, when we have secant derivative of integral of secant, it gives us something like pretty odd, like ln of secant plus tangent. That's not something that we want to use because now we have secant again. And we had to figure out how to get rid of that. Like we want the entire expression just tangent or just cotangent, right? We want to put it in polynomial form. So we can use another integral. Secant tangent dx is now just going to be secant itself. So now everything just becomes secant. Because with the other one, you can use this expression to manipulate. So let's see what we have here. If we put u as secant, you have du is going to be secant tangent dx. Do the change of variable. Secant of 0 is 1 because it's 1 over cosine of 0 is 1 over 1. Pi over 2. So it's a pretty bad one here. We put it as pi over 2. Give me a second. I think I make a mistake with copying down my note. So how do I actually do it if it's pi over 2? Okay, let's change it to pi over 4. Make life, or like pi over 3. Make life a little bit easier. Because, yeah, cosine of pi over 2 is 0, so 1 over 0 doesn't make that much sense. So we have 1 over cosine of pi over 3. Cosine of pi over 3 is half. 1 over half is 2. So the integral now become I is the integral from 1 to 2. Now, we take one secant and one tangent out, so it's going to be du. What we have left is secant fourth and tangent 6. Secant fourth is going to be u fourth. Tangent to the 6, you can write it as tangent to the 6x is tangent x, tangent square of x to the cube. And that one you can this as u secant square x plus 1 cubic. It's going to be u square plus 1 cube. It's a little bit annoying when we have to expand a cube, but that is the better way to solve it, unless you want. There's not actually another way that I can think of that we can solve the problems. Here we have so it's 1 to u to the 4th. Now if we expand this, so another way we use general formula, a cubed plus 3a squared b plus 3ab squared plus b cubed. So this is similar when you try to expand the square. This is the formula that you're going to use to expand the cubic. U6 plus 3u fourth plus 3u squared plus 1. Because b here is just going to be 1 du. So now just distribute them in and solve for it. A lot of my students ask me the questions like, how do I know like these cubic thing to expand? I would say, personally, I don't think your exam is going to be that hard. And the quiz is the same. I mean, I don't interfere with your grades. Doesn't mean that I don't know what your quiz is about. But it's a good thing to know if you proceed further to like other class of math, like 230. I definitely think that you need to use it. 251, if you ever take differential equations, I think some part of it will have it as well. Not a big part. Most of it is using the derived equations, but 230 definitely you're gonna need it. So it's always good to know. But I mean, if you don't know like these things, don't freak out. The life is not that bad. So if you don't know about it, now you know. So it's a good news. So solving for this is u9 over 3, u7 over 7, u6 over 5, and from 1 to 2. So we can do the rest. I don't want to do the algebra here. If you have a calculator, that'll make life so much easier. But other than that, that's all I have for today. Is there any questions so far? I think for this one, there's a lot going on here. So it's normal if you guys don't understand something. I'll put it in the chat room right now so I can answer, or email me during the weekend if you want to go over these videos again. I'll always record these and upload them online. I also send the slides to Dr. Kasha so that she can send it out or put it on Canvas, up to her. But if you have any questions here, let me know. right now so I can help you promptly, or if not, maybe if you want to schedule like an individual meeting with me, feel free to let me know what time works for you. If there's nothing else, then I'll end the sessions here. Then some of the practice questions as I change this part, I'll send you guys with the updated link. Okay. Yeah, and you're welcome. So yeah, these are the practice problems I have here. They're gonna be more coming, and especially for the midterm week. So how I run the midterm is that I'm not gonna do the exam review. Dr. Catcher is gonna do it, but I'm gonna have some of the practice questions in the practice exam that you guys have that you guys feel a little bit challenging, because I will look at the grades that you have. I don't interfere with them, but I'll see how you guys perform on it. I'll pick some of the hardest questions that you guys usually get wrong, put it in the practice exam, and work on it. I will also have around 26 problems to prepare for each exam. I try to use like every character in the alphabetical order, but yeah, that's around 26 of them. So don't freak out when you see the end of my slide, because they have a lot of problems to work on. If you don't see Dr. Kasha send out these slides and PowerPoint, send her an email, because I always send them to her, but I don't know where she put them. I don't actually check back of where she put them on Canvas. Maybe sometimes she forgot as well. So yeah, email her about that if you want to. And then if you have any questions, if you don't have any more questions, I'll end the sessions here, and I'll see you guys this next week. Have a great weekend. You're welcome.